So, in our crazy complex world, how do you even begin to predict what's going to happen, especially without spending a fortune on real world tests? Well, there's this really powerful technique called discrete event simulation. And we're going to see how it works by, get this, cleverly ignoring most of time itself. Sounds weird, right? But it's brilliant.
Right, so here's the core problem we're all trying to solve. I mean, we are surrounded by systems, right? Just collections of things interacting with each other over time. And we always want to ask, what if? What if we change the layout of our store? What happens if our website traffic doubles overnight? How can we possibly get answers to these questions without just, trying it and hoping for the best? That's expensive and risky.
Okay, let's start with something we can all picture. A super busy coffee shop. You're the manager. You want to know things like, how long are people actually waiting in line? Are my baristas totally swamped? And the big one, should I hire another person? Sure, you could stand there with a stopwatch for days. Or you could use a model that lets you test out all these different scenarios in an instant and get your answer.
All right, now let's scale that idea way up. Instead of a coffee shop, think about a factory assembly line. We're talking dozens of stations, machines that could break down, workers who have good days and bad days. Trying to design that efficiently, that is a massive challenge. This is where simulation becomes absolutely essential, because you can find all the tricky bottlenecks before you've even bolted a single machine to the floor.
And then, what about the systems you can't even see? Take a computer network. You've got millions, literally millions of data packets flying between routers every single second. How in the world do you test a new way to route all that traffic? Or predict how the whole system will hold up if there's a huge spike? Yeah, for that, you need a really clever approach.
So, how do we do it? How do we model these enormous, complex systems without our computers melting? Well, the secret isn't just throwing more powerful hardware at the problem. Nope. It's about a completely different way of thinking about time itself. We're not going to watch the clock tick. We're going to learn how to jump through it. I mean, you could try to simulate every single nanosecond of a system's life. But just think about that for a second. That's a ton of wasted effort, right? All that processing power being burned when nothing is actually happening. This is where discrete event simulation, or DES, comes in. It takes a totally different road. It only bothers to simulate the moments that actually matter, the events. So what exactly is a discrete event? It's just an instant in time when something important happens, something that changes the state of the system we're looking at. Think about it. A customer walking in the door. That's an event. A barista handing over a coffee. Event. A little data packet arriving at a router. Yep, that's an event too. Each one is a single, instantaneous moment. Here's a great way to think about it. Imagine you're a railway station master. Are you sitting there watching the clock tick every single second? Of course not. You only care about two things: when a train arrives and when a train leaves. All that quiet time in between when nothing's happening on the platform, it's totally irrelevant to your job. Well, DS works in the exact same way. Okay, look at this timeline. This shows the magic in action. See? An event happens at time 0. Now, the simulation clock doesn't just tick, tick, tick forward. No way. It jumps straight to time 1.2 for the next event. And from there, it leaps all the way to 4.7, and then again to 5.3. All that empty space, all that nothing time in between, the simulation just completely ignores it. And that is the secret to why it's so incredibly fast. All right, so time jumping sounds pretty cool, but how does the simulation actually know where to jump next? And what's it supposed to do when it gets there? Good questions. Let's pop the hood and take a look at the engine. So inside any DIS, you've basically got 5 key parts working together. Let's think of it like a project manager's setup. First, you have the system state. That's just the current status report. How many people are in the queue right now? Then you have the events themselves. Those are the tasks. The event list is the crucial part. It's the to-do list, all sorted by time. The clock is, the clock. And finally, the scheduler. That's the project manager, the brains of the operation, that pulls tasks off the list and gets them done. And all these parts work together in a really simple, elegant loop that just repeats over and over. Step 1, the scheduler grabs the very next event from its to-do list. Step 2, it jumps the clock forward directly to that event's time. Step 3, it processes the event, which updates the system state. And step 4, and this is so important, that event might create brand new events in the future. So when a customer arrives, that might schedule a new finish making coffee event for, say, 3 minutes later. That new event just gets popped into the list in the right time order, and the whole cycle starts again. So, That's the theory. Kind of neat, right? But where is this stuff actually used in the real world? The answer might surprise you. It's pretty much everywhere.
When you're talking about mind-bogglingly complex systems like computer networks, DS isn't just a nice-to-have, it's the only way to do it. It is the engine that powers all the big-time network simulators that researchers and engineers are using right now. I'm talking about tools like NS3 and OMET++ to literally design the future of the internet.
But let's bring it back down to our coffee shop. It's so easy to see the power here. On the left, we've got one barista, and whoa, look at that line forming. Now on the right, we just run the simulation again, but this time we've added a second barista, and boom, the queue is way shorter. DES lets you do these what-if experiments totally risk-free, giving you real data so you can make smarter decisions.
And it's not just cafes and computer networks. The applications are just huge. It's used to design massive supply chains, to figure out how your computer's operating system juggles different tasks, and even to model how a disease might spread through a population. Basically, if you can describe your system as a series of events happening over time, DS can model it for you.
So what's the big takeaway here? If you're going to remember just one thing about all this, what should it be? It really just boils down to a single powerful word: efficiency.
Seriously, if you walk away with one thought, let it be this one. At its core, discrete event simulation is all about the power of skipping the boring parts. That's it. Its true genius is that it's smart enough to completely ignore all the dead time and only focus on the moments that actually change something.
And why is that such a big deal? Well, because that incredible efficiency gives us scalability. It means we can model systems that are so huge, so complex, that it would be totally impossible otherwise. And that scalability gives us something even more valuable: insight. It gives us a virtual laboratory where we can pray, experiment, and innovate without any of the cost or risk of the real world, whether you're trying to fix a hospital waiting room or design a global shipping network.
So by letting us peek into the future of these complex systems, discrete event simulation really gives us the power to make them better. It's an incredible tool. Which leaves just one question, really. Now that you can model almost anything, what problem are you going to solve first?